All right. Good afternoon, everybody. And for those of us joining us on the East Coast, good evening. My name is Colton Marchessault. I am the program director for the Arizona chapter of the Vertical Flight Society. I want to go ahead and let you know right now that we have basically everybody's cameras turned off and all audio. And I'll give you a breakdown of what the schedule is going to look like in a minute for the rest of the evening. So first off, thank you everybody who's in attendance, because this is our very first virtual event that we're going live on. And we are, of course, collaborating with the Redstone chapter as well as the Philadelphia chapter. So thank you again for your members who are attending tonight. We intend to host a few more virtual events as the year goes on and possibly into 2021. So we're looking at bringing on some additional speakers, not only in September, but October and possibly November or even December as the year goes on too, to see who's available and whatnot. VFS Arizona may not necessarily put all of those on, since we will be collaborating with the Redstone and Philadelphia chapters, but we will of course send out more information as those are created and as more information becomes available. On top of that, we have a couple more general events going on in the year. We have the Forum 76 conference, which is entirely virtual, coming up in October. And then moving into the early part of next year, we have our eVTOL conference. More detail is coming out on that right now. We're deciding if it's going to be entirely virtual or if we're going to have it in person, so stay tuned for more information there. At this time, I would like to welcome Ada Walsh from the Philadelphia chapter to go ahead and say a few words about the Philadelphia chapter's upcoming events or any other announcements she has. So Ada, if you're online and if you can hear me, you have the floor. Go ahead and take a minute and tell us what's going on.
Hey Colton, can everyone hear me?
It's a little quiet, but we can hear you a little bit.
Okay, I'll speak up. Hey everyone, I am Ada Walsh. I'm the publicity chair for the Philadelphia chapter of VFS, and hopefully your next dinner meeting chair. I just wanted to give everyone a heads up that the elections are kind of in the process of happening, so just be on the lookout for any of you Philadelphia members. Be on the lookout for your email, because correspondence will be coming out for that. And we don't have any events planned right now, but we're working on that, and hopefully, yeah, we can continue working with other chapters for these virtual events, which I think has been great. And if anyone wants to speak at an event, reach out to me and we can get something started. So that's all I had.
All right, thank you very much, Ada. It's finally nice to speak with you. And then we'll do the same thing from the Redstone chapter now. We'll turn it over to Bill McCandless. And Bill, if you want to do the same thing, say a couple of words, the floor is yours.
Right, I'm going to turn on the webcam to match a face to the voice. I'm Bill McCandless. I'm out of the Redstone chapter. I'm the current vice president. I'll be the president of the Redstone chapter come January. Most of our membership, but we have about 250 folks in and around, centered around the Redstone Arsenal area. Right, so we have a heavy emphasis on the Army programmatics and the big pushes for FAR and FLRAA here for future vertical lift. So you see a lot of that coming out of the Redstone area. The biggest thing on the next thing on our agenda is the annual Berry Basket golf tournament on September 11th. That funds the Redstone chapter scholarship program. So we've got a good turnout so far. Everyone doesn't mind being in their own cart to go play golf for the day, it seems. So we're getting ready for that event, and that's usually a big fundraiser for us. And then we're looking forward to being part of the co-host here. We're thankful you guys invited us. We think it should be easy to find somebody every couple of months to come out and give this nice broad view to folks. And we're excited to be part of this presentation tonight and look forward to hosting one in the near future. So thanks for the chapter members that are out tonight. And again, thanks for having us.
Awesome. Really appreciate you guys being here. This is it's pretty big, and I'm not going to lie, I'm a little nervous to be doing this, but very, very proud of the progress, I guess, that we have made forward going with this whole collaborative effort. So again, thank you to everybody who has made this possible. So before we get started real quick, I want to go over a brief agenda of kind of how the presentation is going to look and what we want to do to interact with some of our viewers. So in about a few minutes here, I'm going to turn it over to Dr. Rajan. I will refer to him a couple of different times as Subi. And what we will do is we will allow him to present for about 30 or 35 minutes. At that point, we will turn it into about a 10-minute session for Q&A. And that's where we want the participation to come in. If you guys would like to ask questions to Dr. Rajan, please feel free to submit them via the chat box. Go in there, type up your questions. Please realize that because we are very limited on time tonight, trying to be respectful of everybody's schedules and how late it is in some other time zones, we can only answer so many, and we're going to try our best to stick to the 1 hour threshold that we have right now. So at any point, if you guys do have a question, please go into that chat box, type it in. And when we get to that Q&A session, I'm going to go through and kind of read out as many questions as we can possibly get through until we either have no more time or until we run out of questions. So with that being said, I do want to talk very briefly about Dr. Rajan. So he is a professor at Arizona State University. He began his academic career there in the fall of 1983. He's presently a professor in the School of Sustainable Engineering and the Built Environment. His research and teaching interests include the general area of finite element analysis and design optimization. He is the director of Computational Mechanics Lab, where algorithms for high-performance computations are developed and implemented. Dr. Rajan has worked on research projects sponsored by government agencies such as NSF, NASA, FAA, ARO, and FHWA, and private companies such as Motorola, Honeywell Engines, SRP, Tyco International, Alcon, and HYI, working in diverse areas as design optimization, parallel processing, constitutive material modeling. There's a lot going on here. Microelectronic packaging, web-based distance learning, impact mitigation, biomechanics, engineering software development, and Dr. Rajan is the author of several books. And I think with that, we're going to go ahead and turn it over. So welcome to Accelerating Towards Design by Analysis for Composite Aerospace Structure. And Subi, you have the floor, sir.
Thank you very much, Colton. I really didn't want to give you that long bio about myself. But anyway, thanks for the introduction. And I'm very pleased to be here talking to people who are essentially working in my backyard, who are my peers and so on. So we definitely would encourage you to ask questions as I go along. I don't want to be speaking for more time than I'm allocated. So Colton, if you'd remind me about 5 minutes before my time is up, because there may be some slides that I may skip over if time is a big issue.
Yes, and I will do that by turning on my webcam. And if I get a break in the action, I will also make a quick comment via the microphone.
Thank you very much. So I have divided my presentation into 3 parts. First is I'm going to talk about impact mitigation in general, where composites are used to take care of a projectile that is hitting a target at a high speed. And then I'll talk about the ingredients that we have used at Arizona State University with my team and my collaborators in other universities and other government agencies. So I've had the opportunity to work, as Colton said, with the FAA and NASA primarily, and then a number of other educational institutions. And then I'm going to discuss 4 case studies. 2 of them deal with aerospace type of composites, and the other 2 deal with impact mitigation for body armor and for football helmets. So let's start looking at the use of composites in aerospace. I don't have to tell this community where composites are used in the aerospace industry. All of you know that one of the most well-known companies is Boeing, that uses an extraordinary amount of composites in their latest generation of aircrafts, and that has led to a variety of advantages in terms of using less fuel, in terms of being able to fly longer distances, and so on and so forth. So I'll put that on the side, and then I'm going to discuss a little bit about my history getting involved with research in the area of impact mitigation. So back in 2001, I was introduced by one of my former PhD students who was working for Honeywell Engines in the Phoenix area to the members of the FAA team that was taking care of the engine containment issue. And for those of you who are old enough to know, back in 1989, there was a United Airlines flight going to San Francisco. There was a fan blade out event that took place at 37,000 feet. And fortunately, we had the pilot able to control the aircraft reasonably well so that there was a landing that took place in Sioux City Airport. Unfortunately, 111 people out of the 296 died. And since then, FAA has required all engine manufacturers to make sure that if there is an unexpected fan blade out event, that the pieces are contained within the containment system and they don't sever the other systems in the aircraft, like the hydraulic and the electrical networks that are required for other performances. And big engine aircraft manufacturers like General Electric, Rolls-Royce, Honeywell engines, and so on have made sure, Pratt & Whitney have made sure that the latest generation of aircraft engines are equipped with the appropriate containment system, and they have helped a lot. If you look at the recent fan blade or disc failures that have taken place in the last 5-6 years, you'll find that there are a few of them, and I've listed a few on the screen, and you can see images of some of the aircraft after they have landed on the ground. So we have gone a long way from losing control of an aircraft in highly unpredictable ways because there was no containment system to take care of an unexpected event like this, to having more control over unexpected events like fan blade and disc failures and being able to maneuver the aircraft back on the ground. So I got started doing research work in this area with sponsorship from FAA. They gave us money to start building a constitutive model that would go into a finite element program, and we started working on a finite element program called LS-DYNA, which is a commercial program started by John Hallquist after he left the Lawrence Livermore lab. As a news item for some of you who may not be aware of this, about 3 or 4 months ago, LSTC got taken over by ANSYS. So the LS-DYNA software that I'll keep referring to throughout my presentation today is now a part of a much bigger company. And they now obviously would like to use this opportunity to make sure that other industries that were not using their software are able to use the attractive features in the software. So with that background that I started working on back in 2001, I started looking at other areas. And by training, I'm a civil engineer. So my undergraduate degree is in civil engineering. My master's and PhD degrees are in materials engineering tied to solid mechanics. So I started looking for other areas where I could use this knowledge and come up with new product designs. So what you're seeing on the screen is body armor, and there is an agency called National Institute for Justice that comes out with standards that body armor typically sold to law enforcement people need to follow before they are actually brought out on the market. And you can see the same theme is going to be there in every single industry where composites are used to take care of ballistic issues. So if you want to do ballistic mitigation, there will be competing things that come into play. You want your product to be as light as possible. You want your product to be as thin as possible. You want it to be really cheap. And in the case of body armor, not only you want it to be as concealable as possible, but you also would like to have the user have that wear comfort, so that when a police officer is wearing the body armor, he or she can fulfill their obligations without being borne down, without being weighted down by the body armor. So weight, whether you're designing aircrafts or helicopters, or you're designing body armor, or you're designing football helmets, is the one item on top of the list. So to give you an idea, when you look at the armor that a typical US soldier wears, the total weight of all the stuff that the soldier has to wear is roughly between 100 and 150 pounds. And the two biggest culprits that add to the weight are batteries, because a lot of electronic gear is currently being used by the soldiers. And the second one is body armor. Typically, the plates and the helmets weigh about 30 pounds. So if you can shave 2, 3, 4 pounds, that is an enormous savings in the weight in terms of what the soldier would have to carry going long distances. And that savings in weight may translate into other functionalities that typically is not available because of the weight that the soldier has to carry on the field. So this is a very nice segue into how this idea also applies in the case of sports equipment. And I'm going to use the example of American football to illustrate that the impact that you see with fan blade out event or with body armor is also borne out in sports equipment. And people have been ignoring this for a very long time, but this problem cannot be ignored anymore. There are a lot of news that have come out showing how poorly ex-NFL players are doing, especially the ones that have been subjected to a lot of MTBI or TBI. These are traumatic brain injuries that take place when football helmets impact each other and the head is uh, subjected to uncontrollable forces. So between 1869 and 1905, there were 18 deaths and 150 serious brain injuries. But lately, when you look at the previous data, they didn't have CAT scan data available, but now CAT scan data is available. So you clearly can see the trauma that these football players have gone through. And this is something that I've taken from the PBS website, which says Troy Aikman in the 1993 season was subjected to a big hit during a game. He took a knee to the head, and he still doesn't remember that game at all. So you can see impact mitigation in terms of sports equipment is extremely crucial, and people below a certain age should not be engaging in rough sports like this. So let's look at the key ingredients. With that background out of the way, what key ingredients are necessary? There are a lot of key ingredients necessary when you're working for a multinational company that does helicopter design or aircraft design or armor design or automobile design. There are suppliers, there are subdivisions within the company that engage in a multitude of things, especially with respect to materials and composites. So I have listed 4 areas that are on top of the list. I'm not a materials manufacturer, the raw materials manufacturer. I will show you an example of body armor that I was involved with in terms of the manufacturing process. So I'm going to touch less on raw materials and manufacturing. And given the raw material and manufactured raw material, how can we use those in order to characterize the material properties by doing material characterization tests and structural tests, and then use that data in building in computer models that have reasonably good, if not excellent, predictive capabilities. So we want to go through a process by which we can design products on the computer and postpone testing, actual laboratory testing or full-scale testing as much as possible. The last topic which I've listed on the screen is design principles. Design is an extremely complex area. I'll not get into it, but I will talk a little bit about optimization and using optimization techniques in the context of design of products towards the end of my presentation. So at Arizona State University, we have reasonably good, if not excellent, testing facilities. On the screen, you see a variety of test fixtures and testing frames that we use for testing. So on the left, we have an MTS test frame with a capacity of about 22,000 pounds. We have an Instron machine where the capacity is roughly 110,000 pounds. So we can test materials and take it to those levels of loading if necessary. So these are a number of fixtures available to test the specimens in tension, in compression, in shear, and we can do these simple ASTM type of tests or more complex tests for which there are no ASTM standards. And we use digital image correlation to get full field displacement field that we then convert into strains, and we use that to find out the stress strain curves and other properties of interest. In addition, we have high-speed cameras that we use to capture events where the duration of the event could be just a few milliseconds. We have used this to test Kevlar, which I'm going to discuss a little bit as a part of the engine containment system. So we take a piece of Kevlar, put it in a hydraulic system, pull it at a very high rate, use this camera, get the strain field, and then do the data analysis. And finally, we also have access to excellent optical and scanning electron microscopy that we use to find out exactly what's inside the material before it is tested, which I'm calling here as the virgin specimen, and after it is tested to show what are the different type of damage and failure that can take place inside the material. So here you can see matrix cracking, here you can see debonding between the fiber and the matrix. So one material that we have analyzed a lot, that we have tested a lot, that is used quite ubiquitously in the aerospace industry is a unidirectional composite manufactured by Toray Composites called T800F3900. This is a composite which has a carbon fiber and a proprietary epoxy system. And we have used this to build the process by which we can characterize material. So here you see the optical microscope images and the SEM images for this material. Each filament in the carbon fiber is roughly 5 microns. And you can see hundreds, if not thousands of these in each layer. These are the different layers in the laminated composite. These are the resin-rich zones. And you can see here, we make a lot of assumptions when we do the analysis, when we build the model, but in reality, these assumptions are not actually borne out when we examine these materials in very close, in high magnified zones and look at it very closely. So these are the material properties that we have found. Some of them are from the manufacturer, others are from testing in the laboratory. So I'm going to quickly walk through and show you some of the testing that we do to get material properties. So on the left is the iso-PESQ shear test that is being done. And on the right is a tensile test that is being done in the one direction where the fibers are. And all the colors that you see are different strains being measured by the software, the DIC software. And on the left, the shear test is stopped when we run out of room in the test equipment to carry the test further. And on the right, we get a very nice crack in the gauge section in the center of the specimen. So we have reasonably good, reliable data available to us to build our constitutive models. So this is another example of how you would characterize a laminated composite. This is a double cantilever test being done to find out what are the properties in between two layers of the composite, the two lamina, so to speak. And then the test results, the DCB and the end notch flexure test results give us additional pieces of information to put into our computer model. Now, these computer models, fortunately or unfortunately, are extremely expensive to run. So we have a high performance computing center where we run our computer models. So there are 4 case studies. I'll quickly go through the first one, which deals with the engine containment system. Most of the testing, high velocity impact testing, was done at NASA Glenn Research Center. You can see the gas gun on the top right. And we have a 40-inch steel diameter ring wrapped with layers and layers of Kevlar. There is a cutout here where these 2 projectiles are going to hit the cutout. So in other words, these projectiles are going to hit against the Kevlar layers. And the objective of this exercise is to see how good the computer model is in predicting this impact event. So this is the computer model here. So we have the steel ring shown in gray. We have the Kevlar shown in gold. And the LS-DYNA material model that we developed for this, for dry fabrics, is called MAT 214. These are the 2 models of the projectiles that I showed you in the previous slide. And then we take it and run it. So on the left are high-speed camera images from NASA Glenn Research Center that shows that with this configuration, the projectile is uncontained. And on the right are our computer predictions. So there are 2 computer models here, and both of them do a reasonably good job in predicting exactly what the exit velocity of the projectile is, which is the gold standard in measuring how good the computer model is. So you can see here in this case, the projectile velocity is roughly 889 feet per second. Now, the reason why I had the title in terms of saying design by analysis is because FAA allows certification by analysis, provided you can show that your analysis models that you're using have reasonably good predictive levels, so you can cut down on the testing. So anecdotally, I've been told by people at Honeywell Engines that doing a full-scale testing of one of their engines runs anywhere between $5 million to $10 million, and they would obviously like to minimize the number of full-scale testing that they do. So obviously, if you have a good predictive model, computer model, then the cost is extremely minor compared to carrying out a full-scale testing. So the second test case that I'm going to look at is a much more involved project that we have been working on since 2013. This is what I'd like to refer to as the mother of all composite models for impact analysis. So this material model implemented in LS-DYNA has been implemented with funding from FAA and funding from NASA as a part of the Advanced Composites project. It started in 2013 with funding from NASA. From 2015 to 2018, we received, with FAA, and 2015 to 18 with additional money from NASA. And since 2018, FAA has continued to work with us and provided funding. So the other entities that are involved in this or were involved in this was George Mason University and Ohio State University. Ohio State University has excellent testing facilities to do rate-dependent testing, and George Mason University collaborated with us to implement the theory behind MAT 213 in the LS-DYNA program. So once again, we relied on NASA Glenn Research Center to give us their test facilities and generate data. So in this case, the projectile is different. It's an aluminum piece, roughly with a mass of 50 grams. So this is the hollow aluminum piece that hits a 12-inch by 12-inch composite panel. And in this particular case, we have taken the T800 F3900 composite, 16 plies in 090 plus minus 40 configuration. So the total panel thickness is roughly 0.122 inches. So on the left is the panel before it is tested. On the right is the panel after it is speckled. So a spray is a spray from a spray can of paint is used to paint the front and the back surfaces of the panel. That is then used by the high-speed cameras. Information is gathered, and then DIC is used to find out full field displacement that is then used to construct the strain field. So they did a total of 14 tests, out of which 11 were contained and 3 were uncontained. And I'm going to show you an example of 2 uncontained tests, one where the damage is not visible to the naked eye, and the other one where the damage is visible to the naked eye, and show you how MAT213 or how the LS-DYNA program has been used as a predictive tool. So on the left, you can see here is the prediction from the computer program. On the right is the high-speed camera used at NASA to capture the event. So you can see in this case, there is damage inside the material, not visible outside. The projectile is contained, it goes back. And we have the same thing available to us in terms of the computer simulation. So here I'm showing you different snapshots. This is the snapshot of the projectile hitting the plate, looking bottom up. On the right is looking at the rear side of the panel where we can see what the Z displacement is. And here we are comparing the computer prediction against the experimental data. So the peak prediction and the time where it occurs are reasonably close to each other. And we have here pictures showing what the percentage principal strain is on the plate coming from the computer program versus what the DIC data tells us. You can see a little bit of damage here, but otherwise most of the plate is intact. So after the testing was done, NASA took apart this plate, did ultrasonic scan images to come up with a diagram that shows where delamination occurred in those 15 layers in between the 16 plies. And these are the predictions coming from the computer program. So when you look at the full simulation model, this is the area where we do see delamination in the model. This compares reasonably well with what we see with the ultrasonic scan. Ultrasonic scan will not tell us where the actual delamination is, but we can get that information from the computer model. For example, layer 4 shows this is the region where we have delamination, layer 5, layer 7, layer 9, and so on. So we have more fidelity available in the computer model that's not available in the experimental result. So this is an impact at a much higher test where there's considerable damage, but the projectile is still contained. And here are the computer predictions. This is the rear view. This is the front view. This is where the impact takes place. This is where you can see the backside of the panel, the cracks that have taken place. And we can now compare them against the photographs that are available after the impact. So this is the plate after the impact, close-up of the damage around the point of impact. These two show the computer predictions and reasonably close in terms of what we have been able to obtain. So my last two, I'm assuming I have about 5 or 8 minutes left. I want to spend a little bit of time to look at something that may be of interest to all of us, only because we can understand these things slightly better. There are interesting stories behind these two examples that I'm going to discuss. So the first one I'm going to discuss is the design of personal armor protection system. So for about 10 years, I worked for a company called Armor Designs in the Phoenix area. That company was set up to come up with body armor for law enforcement and also for the US Department of Defense. So the example that I'm showing you on the screen is an example of NIJ level 3 body armor plate. So the culprit in this case, or the competing things in this case, would be weight, cost, how thin it is, how comfortable it is to wear. And this goes back to 2010, 2011 timeframe, where we came up with the lightest NIJ level 3 plate weighing roughly 3.2 pounds. This was able to easily defeat 6 shots of M80 round shot at roughly 2,780 feet per second. So there are 6 shots that take place in this armor, and the computer model that we used was only for 1 shot, and we were reasonably sure that if you are able to defeat that shot using the actual produced armor, then it would take care of 6 shots, and that was the case. And it was relatively thin, 1 inch. This is hard armor. There are other types of armor that defeat lower threat levels, which are soft armor. So here is the LS Dyno model. This is a cross-sectional view through the armor plate. Much more number of nodes and finite elements in the region of interest, less away from it. This is the cross section. You can see the bullet starts off undamaged, and at the end, the bullet is completely captured in the body armor. This is an actual armor that was shot, and where the bullet is completely gone, there is a little piece that you can see here. And we got this cross section by using water jet to cut the plate after it was shot at one of the certified testing places. So this is the comparison between the finite element prediction and the actual ballistic test. So there is a fair amount of work that needs to go into building the finite element models. I don't want to give the impression that building computer models is extremely easy, that there are no issues. There are lots of issues that you have to resolve. Here we used coarse, fine, medium, and fine finite element models. By putting in more finite elements in the model, you get better fidelity in the model, but at the cost of greater compute effort. And in each one of these cases, we use 2 metrics to see how good the prediction is. The first one is called back phase signature. So NIJ standard says if the back phase signature is greater than 44 millimeters, the plate has failed the test. That means for a typical person, if he or she is wearing a body armor and the bullet is arrested within the armor, but the back phase signature is 44 millimeters or more, it's going to leave a huge mark on the skin, and it is possible that the internal organs may be damaged. So that is the reason why you want to limit the back phase signature to 44 millimeters. Why it is 44 is that's another webinar, but that's the standard we have to follow. So our prediction showed that we could capture the bullet and get a number of undamaged layer and get a back phase signature of roughly 36 millimeter when we looked at all the 6 shots, and the ballistic test showed that the actual back phase signature was 40 millimeters. There were 35% of undamaged layers was 35. So if you go back and look at the previous slide here, these are the layers that are undamaged, and the computer model says that 30% of the layers were undamaged. So again, reasonably close to what the actual test results showed. So time for the last example. The last example talks about football helmet impacts. So one of my master's student who is now working for Honeywell Engines took this on as a master's project. He used the same laboratory that we have. Some of the equipment in the lab was used to characterize the material inside a typical helmet. I believe this is the Riddell Revolution attack helmet. And unlike the other models and unlike the other examples that I've discussed, here the football helmet is repeatedly used without being completely damaged. So that creates additional challenges in terms of how you can design a football helmet to take care of minimizing the effects due to the high acceleration that takes place during an impact event. So there is an agency called NOCSE that has standards for head forms, and they come up with guidelines by which you can see whether the helmet is properly positioned on a player or not. So we built the computer model. We did not take two individuals or two players hitting each other. We mimicked the hit by using a solid impactor, which is a steel plate or steel block that you can see here, or an aluminum block, whatever block you want to do in your drop test. This is the finite element model containing all the components, the shell, the solid hard foam, and the solid soft foam. If you're interested, this computer or this journal paper gives more details on how this model was built. What did we do to instrument the model in the lab to see how well the predicted capabilities would be, and then use this model for the helmet in the actual impact testing. So this is a full human body model that is built by a consortium called Global Human Body Model. This is a consortium of automotive manufacturers and a number of universities involving biomedical programs. They have different models for different parts of the body. All these material properties have been coded for an input that works with LS-DYNA program and a number of other finite element programs. You can see this model has very high fidelity. There are more than 2 million elements for the entire body. So we took the body model, then we put the helmet, and then we took this impactor and we did two simulations. One is a crown impact simulation, and the other one is the frontal oblique impact simulation. And then we looked at the strain levels. I was very fortunate to work with one of my colleagues who is a biomedical engineer, and he does this for a living. He understands exactly how to characterize what is going to cause MTBI and what its relationship is to how the human body actually sees strains and strain rates. And now we have a model that is extremely predictive. To get an actual data for a human being is impossible. We cannot do that, obviously, for very obvious reasons. But then how do we have some confidence in the computer model and use this as a predictive tool? So we can go inside the model and find out exactly what the strains are and what the strain rates are. So the brain stem, the midbrain, the corpus callosum can all be queried by going into the computer model to see exactly what the values of strain and strain rates are.
Okay, are you still there?
Yes. Okay, so I'm assuming this 5 minute.
365.
Okay.
683.
Oh, Colton, I see your voice is being heard. So I'm assuming my time is almost up, and this is my last slide. I want to acknowledge a lot of people who have helped me over the last 30, 40 years of my work in the area of high performance computations in terms of finite element analysis, doing laboratory testing, building computer models, doing computer coding. I definitely want to thank the people at Federal Aviation Administration who have funded my group since 2001, Don Altabelli and Bill Emmerling. Bill Emmerling recently retired. Don Altabelli retired about 4 or 5 years ago. They trained Dr. Dan Cordasco, who is an excellent individual, who is now funding the research work and is a technical manager. The other entity that I want to acknowledge would be the NASA Glenn research people, especially Doctors Rob Goldberg and Mike Pereira. Mike Pereira is the one who's done all the impact testing at Glenn Research Center and has worked with us very closely in sharing the data and giving us insights as to how impact takes place and what really needs to go into the computer models. Then in terms of my personal body armor type of work is concerned, I want to thank Honeywell International, based out of Richmond in Virginia, Dr. Ashok Bhatnagar, who is a technical fellow for Honeywell. He has funded some of my research work and has worked very closely with me, especially when I was working with armor designs. And then obviously a multitude of my graduate students, colleagues, and collaborators in different universities. And with that, my presentation is over. Thank you very much.
All right. We're troubleshooting with some people, trying to get them in last minute, but thank you very much, Subi. So we're going to move over to the Q&A real quick. Got a couple of different ones in here, and I guess I need to pull up my chat window again, wherever that went. Okay, so we got two of them, so we'll start with the first one. So what would be the rough cost estimates of running a full blade failure analysis like the one you showed?
Wow, these are difficult questions. Whenever you talk about cost, it is very nebulous. So let me explain. We have written a user guide for MAT 213. In that, we explain the different steps that you have to go through before you have some amount of confidence in your finite element modeling and can use that as a predictive tool. So the first requirement is you need to know the material properties. So there are a suite of tests that need to be done at quasi-static room temperature conditions. If your composite has rate dependent and temperature dependent properties, then additional testing must be done to get those properties. There is a very interesting phenomena called Taylor-Quinney effect. In Taylor-Quinney effect, when a projectile hits a composite, the composite is locally heated, and you can get, because of that heating, plasticity locally in the material. So we have the capabilities in MAT 213 to take care of that. Then we have to do a number of tests if you want to capture events where there is damage, but very little failure that is visible to the naked eye, because that type of testing will help you build the damage component in MAT 213. And the additional testing that you need for now, for example, the delamination properties, those will be additional testing. Then you take all that and you run through and do single element and multi-element testing. And we obviously will help anybody do that using LS-DYNA program. So you can see exactly whether the data that you input to the program is exactly what the computer program is able to reproduce. Once that is done, then you can start building the bigger finite element models and run it. For example, the impact testing that I showed you for the flat plate, we ran computer models all the way in excess of 1 million finite elements. And then we found beyond a certain point, we reach a point of diminishing returns, so we can cut down on the number of elements, and then we have greater confidence in the finite element model. So whoever has asked that question, I hope I have given you some sense as to how much of manpower is going to be needed in qualifying a material. I'm reminded of a conversation I had with a Pratt & Whitney technical fellow. I asked him as to how much money he estimates is used in qualifying titanium and other metals that Pratt & Whitney typically uses in their aircraft engine system. And the number that he gave me was in excess of $50 million. So if you are moving away from one material to another, and that new material has not been qualified at all, there is obviously some amount of money that is needed in order to qualify the material and then keep on moving forward.
Okay. think it was fairly in depth. I think that answered the question. So real quick, a quick note to our other organizers and panelists, if you guys do answer any questions or anything like that, feel free to share your webcam at this time, just for clarity in who's talking and everything. So Subi, you're also welcome to do the same here in a second, but that's completely up to you.
Okay, I will do that right now.
Sure. Okay, got a few more, and I'm trying to make sure that we're still keeping the time. Looks like we've still got about 10 minutes until it's 5 o'clock here and probably 8 o'clock elsewhere. So we'll take about 5 more minutes for Q&A, and then we'll do some closing remarks and move on. So the next one I have for you is, do the same technologies and results scale to vehicle/helicopter size? Certainly ballistic protection represents significant weight impacts to designs.
Oh, absolutely. When we there are some information I obviously cannot share with you because of non-disclosure agreements, but NASA has tested much bigger panels. I believe they are roughly 4 feet by 4 feet. So yes, these models should scale. The aircraft engine containment system, I showed you one of the models built by the FAA folks. I was working with the Honeywell folks in the Phoenix aircraft engine division here in Phoenix. They built the finite element model for their engine full-scale model. Then they took a Kevlar fabric, wrapped it around their containment system, and were able to do an entire engine simulation. One of those papers is available that shows you what happened at the end of the test. But yes, these things are definitely scalable. If they don't scale well in terms of going from small scale testing that are used to validate the material model to full scale aerospace or aerostructure components, then it would be a terrible shame. Then they simply lose their predictive capabilities.
I gotta remember to unmute myself before I talk to nobody. That was Bill's question, obviously. I'm glad he popped his webcam on real quick, so hope that was suitable, Bill. Might be muted, so. Okay, so we're gonna go over to the questions pane real quick. We got an asker, Ron Olson, and he asked, what NDT ultrasonic method did you use to map the damage out?
Okay, so that information, I believe, is called A-scan. This was done at NASA Glenn Research Center. If you shoot me an email, I can give you the details. That was not done at Arizona State University, but that's a non-destructive evaluation technique using ultrasonic scanning. I believe that technique is called A-scan, and you do get information in terms of how much of delamination is there. But if you use a more refined technique like CT scanning, then I believe it is possible to know where the delamination is in between layers and so on. But that, I believe, is still in the nascent stage. It's not available for routine uses on bigger samples.
Okay. Oh, okay. Subi, I have his email, so I'll have you two exchange emails probably afterwards. I'll keep this on record for me, and I'll shoot that over to you. Okay, on to the next one from Surya. I hope I'm pronouncing this correct. Surya Madan. And Dr. Rajan, do you have any ongoing Fury projects? I believe this is an ASU student in our ASU chapter.
Absolutely. I have Fury projects left, right, and center. It's just that it's a two-way street. So if you get in touch with me, I'll be more than happy to involve you in my projects. Absolutely. We are looking for people to work in the lab, and also we are looking for people to run computer simulations.
Okay. All right. Let's see. We got about 1 or 2 more minutes real quick before we do this. So I guess we'll move over to one of our other last questions. So let's go back up. Can you talk about some of the challenges of building the finite element model? Is it just a trade-off of complexity versus resolution?
No, the complexity is in building the model. Okay, I'm going to use the term build in a very wide sense. And it's going to be appropriate because I'm going to give you a 10,000 feet look into what is meant by a computer model. So a computer model has the geometric data, where you can have errors. Then it has the finite element mesh, where you can have discretization errors. Then you have material constitutive modeling errors, and that's a huge part in all of these. And then you have errors in terms of boundary conditions and loading. So there are different sources of errors that play a big role. In addition to this, we also have errors in running programs on big clusters. So single precision versus double precision, those numerical issues also play a very big role. So yes, there are different sources of errors that you have to be mindful of and take those into consideration. So that is the reason why every single time we make any change, we go through validation test over and over again. So having said that, I'll make my last statement for the day, since there is no more time for asking questions. If you take a room and there are 20 people in the room, and the person who's making the presentation is an experimentalist, there are 20 people in the room, including the person making the presentation. The presentation is an experimentalist. There is one skeptic and there are 19 believers. If you take the same room and have 20 people in the room, and the person who is making the presenter is an analyst, then there will be 19 skeptics in the room and one believer. So don't believe all the experimental results that you see, because there are a lot of times when if you want to have a statistically sound information, you have to do several tests. And there are a lot of times when repeating a test in the experiment will not give you very similar results. You may get something very different. So you have to be a little bit careful here, extrapolating experimental data, both which are used for validation and for material characterization with computers. So what do we do in computers? We use probabilistic theory and we build probabilistic finite element analysis, which adds another complexity and more computing power necessary to run all your simulations.
All right. Well, Subi, thank you again very much for your time and willing to put all this information together for us to sit in and listen to. It's very fascinating, and we very much enjoyed having you. So with that, we'll go really quick into just a few closing remarks. So again, thank you to the other chapters for joining us. Appreciate you guys making it out here for it being 8 o'clock now on the East Coast for you. I do want to turn it over really quickly to my president of our Arizona chapter. She's just got a few words she'd like to say, and then we'll send everybody on their way for the evening. So Tanya, if you're online and if you have your audio connected, please go ahead. Maybe.
How about now? Can you hear me now?
There it is. Yep.
Okay. All right. My apologies. Yes. First off, just really want to thank Subi so much for sharing your work with us. You've made great progress in developing these LS-DYNA models to predict exit velocity of projectiles, and it's very impressive. Your models can certainly help us to minimize expensive testing. So thank you so much for sharing that with us. I do want to ask just one quick question before I acknowledge a few other folks and make some closing statements. How typically long does a computer simulation take?
Okay, so I'm going to give you the latest numbers that I have. So if you run on the ASU cluster, where we have access to roughly 500 tokens, LS-DYNA tokens, that is the limiting factor. So if we don't never use 500 tokens. So if you use roughly 200 or 300 tokens to run the simulation of the impact on the 12 by 12 plate, it can take sometimes 1 day, sometimes 20 hours, sometimes 15 hours, depending upon the event. The easiest ones to simulate are the ones where the projectile is uncontained. So there, the projectile would go through the panel. Simulation time is cut down tremendously, because once the projectile leaves the panel, it's no longer of interest to us. The ones which take longer to do are the ones where there is damage, where there is partial failure, and where the projectile is contained. So roughly a day running, and we don't have the fastest supercomputer at ASU anymore. but that's a pretty good estimate of how long it's going to take.
Wow, that's fantastic. That's great turnaround. Super. All right. I also want to just take a minute and thank Colton, our Arizona Chapter Program Director, for organizing this event along with our Deputy Directors, Philip and Jan. Thank you guys so much for all of your efforts. And also want to just really extend a thank you to the Philadelphia chapter and also to the Redstone chapter for joining us today. I'm very excited that we are taking this new virtual environment and really creating new connections. So excited for what's to come. And then also just really wanted to extend a thank you to Jim Sherman from headquarters, VFS headquarters, as well as Chris for allowing us to use the GoToWebinar for this virtual Tech Talk. And also, I think, Colton, I was having some audio issues earlier, but I think you made a plug for our January 26th through 28th of 2021 autonomous VTOL technical meeting, and also the electric VTOL symposium that's coming up here. It may end up being virtual pending our current COVID-19 situation, or it may be held here in sunny Mesa, Arizona. So be on the lookout for that. We are accepting abstracts right now for the autonomous VTOL technical portion of that meeting. They are due by September 15th. If you have any questions, feel free to reach out to the Arizona chapter. And we're also offering a one-day short course on the electric VTOL design. And that will occur right before the meeting on January 25th. So keep an eye out for that as well. And again, just really appreciate all of you joining. Without you, we wouldn't be able to do this event and make it special. So thank you all for taking your time to join us today.
So thank you, Tanya. Thank you, Colton. Thank you, Ian, for giving me this opportunity. And I appreciate your warm, making me feel at home during my webinar. Thank you.
Thanks again, Subi. Great to have you. All right, everybody. Thank you again for attending tonight. Have a great evening, and we'll talk to you next time. See you later.
Thank you much.
Thank you. Bye-bye.
Good night.